Hello, I'm Professor von Schmohawk, and welcome to YU. So far, we have studied the properties of the four basic arithmetic operations: addition, subtraction, multiplication, and division. In this lecture, we will introduce the mathematical operation of exponentiation. We saw that multiplication is just shorthand for repeated addition. For example, multiplying 4 times 10 is the same as adding 4 tens together. Let's state this in a more general way. If we let the letter n represent any integer and a represent any number, we can say that n times a is the same as adding n a's together. Just as multiplication is shorthand for repeated addition, exponentiation is shorthand for repeated multiplication. A raised to the nth power is the same as multiplying n a's together. To write a raised to the nth power, we write the number a, which is called the base, with a small superscript n, which is called the exponent. This forms an exponential expression. For example, the exponential expression 4 raised to the second power is written as the number 4 with an exponent 2 written as a superscript. Since raising a number to the second power is equivalent to multiplying 2 copies of that number together, which is the same operation one would perform when calculating the area of a square, the number is said to be squared. Likewise, raising a number to the third power is equivalent to multiplying 3 copies of that number together. Since this is the same operation one would perform when calculating the volume of a cube, the number is said to be cubed. Individual exponential expressions can be combined into larger expressions through operations such as addition, subtraction, multiplication, and division. For instance, we can multiply the two exponential expressions 4 squared and 4 cubed, creating a larger expression. We sometimes refer to these individual elements within a larger mathematical expression as terms. Interesting things happen when we multiply exponential expressions together. For example, say that we multiply 4 squared times 4 cubed. Since 4 squared is 4 times 4, and 4 cubed is 4 times 4 times 4, the result is 5 4's multiplied together, which is equivalent to 4 to the 5th power. So 4 to the second power times 4 to the third power is 4 to the 5th power. Notice that we can get this result by simply adding the exponents. This is true anytime we multiply exponential expressions with the same base. For example, multiplying 5 to the third power times 5 to the fourth power is the same as multiplying 7 5's, which is 5 to the 7th power. Once again, we get this result by adding the exponents. So to multiply exponential expressions with the same base, add their exponents. But what happens if we divide two exponential expressions with the same base? Let's try as an example 5 to the 7th power divided by 5 to the 4th power. This is the same as 7 5's multiplied together divided by 4 5's multiplied together. We can simplify this fraction by canceling 4 5's in the denominator and 4 5's in the numerator. After canceling, we are left with 3 5's multiplied together. So 5 to the 7th power divided by 5 to the 4th power is 5 to the 3rd power. Notice that we can get this result by subtracting the exponent of the denominator from the exponent of the numerator. So to multiply exponential expressions with the same base, add their exponents. And to divide exponential expressions with the same base, subtract their exponents. Let's summarize these rules of exponents by using letters instead of specific numbers. To multiply exponential expressions with the same base, add their exponents. And to divide exponential expressions with the same base, subtract their exponents. In the next lecture, we will use these rules to explore more properties of exponents, including the meaning of exponents of 1, 0, or any negative integer.